What does Laplace transform do? Well, that's a very good question. A lot of you might already know that Laplace transform converts a function from its time domain to a frequency domain. However, I think that's a little abstract. The way that I understand Laplace transform is that it simplifies the process of solving linear ordinary differential equations and their related initial problems by converting a calculus problem to an algebraic problem. What does that mean? If we're given a mass Denver spring system, and we know the ordinary differential equation and also the initial conditions, and we're asked to find the response of spring over time. I think intuitively we would think to solve this problem in a calculus way, right? That means writing the characteristic equation, solve for the roots, real or complex, and then from there we will find the general solution and then differentiate that general solution and plug the initial conditions in to find our response of the spring. It's very lengthy, but it works and it's really powerful. However, with Laplace transform, we can simplify this process into 3 steps. First, we would write the subsidiary equation of the ordinary differential equation, and then we can solve the Laplace transformation of y of t. And then we'll take the inverse Laplace transform to find out what y of t actually is. So I'm not saying that calculus is bad. It's just Laplace transform is just a better way to approach these type of problems, and it really saves us a lot of time. And then you might be thinking, what are the application of Laplace transform? One of them is electrical networks. So for example, if you have the voltage input of a circuit and you want to find out what the current is, you can definitely use Laplace transform. Similarly for signal processing. In addition, like what we mentioned, a spring mass damper system, we can also use Laplace transform to help us to find out the response of spring over time. In addition, for fluid dynamics, it's also very useful. If you know the concentration of certain fluids, and then you can look at their concentration response over time as well. And there's so much more. As long as you can model the system with ordinary differential equations, you should be able to apply Laplace transform to help you find out the characteristics that you care about over time. So without further ado, let's start with the fundamentals so we can start solving those complex problems. So today we will look at the definition of Laplace transform, linearity and uniqueness of Laplace transform, and in the end we'll go through basic Laplace transform. So the first one, definition of Laplace transform. So if we have a function f of t and it's defined for all t bigger than 0, then the Laplace transform is just f of s, capital F of s, and the cursive L also represents the Laplace transform, right? I would write like this. And that is equal to the integral of e to the negative st times the original function dt from 0 to infinity. Maybe that doesn't make any sense to you. So here I've prepared an exercise for us to go through so we can understand this better. So for example, if we want to know the Laplace transform of this function f of t, we would write the Laplace of 1, right? That's the function. And that is equal to, from 0 to infinity, e to the negative st times f of t, which is the function dt. Since this is 1, so we can rewrite our equation from 0 to infinity times e to the negative st dt. Here we're going to use some of our integration skills, right? So this, if we take the integral of this function, it's going to be e to the negative st over negative s. And we're going to evaluate this from 0 to infinity. Okay, and I'm going to move over here. So that is going to be, so first we're going to plug in infinity here. So negative s infinity, negative s, minus e to the negative s0 over negative s. Okay, And we know this part is e is also equal to 1 over e to the infinity, and this is going to be huge, so the entire thing is going to approach 0. So we can write 0 here minus, so e to the 0 is 1. So we know that 1 over negative s is the second term. So finally, we can have our Laplace transform of 1 to be 1 over s. So this is how we would perform Laplace transform for any function that is defined for t bigger than 0.